Hi, today I want to talk about space-time and the theory of everything. Well, there are many theories of everything, but in this video we're gonna focus more on string theory. So why do we need a theory of everything? Currently we have a really good understanding of things at the smallest scales, and this is quantum mechanics that describes really accurately the interaction of tiny particles and how these tiny particles, they are the foundation of our entire world. And we have a really good understanding of things at the larger scales, of planets and galaxies and stars. This is the theory of general relativity made up by Einstein. The time where Einstein was alive was a time of many brilliant minds working together on quantum mechanics and also the theory of general relativity. To understand a bit better why do we need a theory of everything, we can ask a simple question. Is the universe analog or digital? Analog meaning smooth and continuous pretty much forever, and digital meaning it is granular or pixelated or voxels, whatever you want to call it. And it turns out that on the fundamental scales, our universe is digital. So when the issues between quantum mechanics and the theory of general relativity arise, is, for example, when we rewind the clock backwards. Currently, when we're looking around in the universe is expanding. And it took a few clever people to ask, what if we rewind the clock backwards? Then you see the universe getting smaller and smaller and smaller. To a time where at one point the universe seemingly had infinite density. An interesting thing to note is that when people talk about the universe expanding from something the size of a pinhead to the size of the observable universe, it is important to keep in mind that they are talking about actually only 1 hour observable size of the universe, not the entire universe. A difficult thing to wrap our minds around is that the universe has always been infinite. So if you take this pinhead, well, what the hell is a pin supposed to mean? Do you mean like an edge of a needle or the ball thing around it? I don't know. Let's say a grain of rice. So imagine that our entire observable universe was compacted into an incredible density inside a grain of rice. But it wasn't the only grain of rice. Besides this grain of rice that contains the density of the entire observable universe in it, there's an infinite extent of other grains of rice in all directions around this grain of rice that also have the same density as the observable universe. And you can rewind the clock back even further of things being even more dense. And that is the point where the theories break down and you get answers of infinite densities. Because then we're going at incredibly small scales and incredibly high densities, so gravity has no idea what to do. We know quite far back, even less than 1 second after the Big Bang, of what happened, that we had incredibly high densities and all the laws of physics were merged into this one superforce before the universe cooled, and these forces sort of crystallized into different laws of physics that we see around us now. Crazy things happened, but if we try to rewind the clock backwards even more, we have no idea what happened. And an interesting thing to note is the theory of inflation, just to get the picture. There is this normal expansion, incredibly rapid expansion of the universe. But now what is also mostly agreed is after the Big Bang there was a time period of inflation. This was an incredible rate of exponential expansion of space itself. And to give some sense of scale, imagine 1 cubic meter of space. And imagine this cubic meter of space expanding into 1 trillion cubic meters of space in a time frame of 1 trillionth of a second. Then in the second trillionth of a second, all of these trillion cubic meters of space, each of them also expands into a trillion cubic meters of space. And in the third trillionth of a second, all of those themselves also expand into a trillion other cubic meters of space. And this is incomprehensibly vast, rapid expansion. This is basically inflation. In reality, I just said cubic meter and I just said trillionth of a second. I said trillionth of meter. But in reality, the amounts are way bigger and the time scales are way smaller. For me, that's one of those mind completely blown moments that, the universe is old and vast as it is, but it's just so crazy to try and understand these kinds of forces of nature and these things happening. It's really weird. And as well, as I mentioned in the theory of general relativity, when we look at black holes, inside of them also are predicted to be singularities with infinite density, and physicists don't really like infinities, so we're guessing that there's something wrong with the theories and we need some way to unify quantum mechanics and the theory of general relativity to understand really dense and really small particles, objects, things, and how they interact. Now I want to talk about the Planck length for a moment. Planck length is the smallest possible length possible in our universe. As I mentioned before, the universe being digital. So to put the Planck length to scale, imagine a dot about the size of 0.1 millimeters, about the smallest thing that our eye can see. Then we magnify that small dot to the size of the observable universe. And then the Planck length inside this dot would be about 0.1 millimeters. So the Planck length is so tiny that in terms of scale, if we could fit our entire observable universe inside this speck of dust, then the Planck scale in that universe-sized speck of dust would be a speck of dust in that universe. Is that confusing? It takes a few moments to really make sense of it. The Planck scale is so small that even the movement of light is granular and digital. If you have two Planck scales, then there is nothing in between those Planck scales. You can't divide space up any more than to the Planck scale, as far as all the theories that we know are telling us. So the thing is that we have no idea how gravity works at these extremely small scales at incredibly high densities. So now enters string theory. So basically out of string theory came particles of gravity called gravitons, and they could possibly explain gravity at really small scales at incredibly high densities. And gravitons sort of naturally emerge from the theory, so you might be thinking, yeah, that sounds good, but an issue with string theory was that for it to work, it required 11 spatial dimensions, and then people looked around, we don't seem to have 11 spatial dimensions, we just seem to have 3, so we need to make some different assumptions. And so one assumption that could be made is that all of these other spatial dimensions are actually curved up really small at the Planck scale. The theory of general relativity tells us to look at space-time as a single entity, as space and time being intimately connected. As the curvature of space also influences the passage of time, that would be an obvious sign that space and time being closely connected. Also, space determines what matter does, and matter determines what space does. So one way to look at space-time is that it's just the curvature of space. So if you have a particle of light moving and it's curving through space, then the path of the particle of light is not actually curving. The path of light is always a straight line. It's just moving in a straight line through curved space-time. So that's one way to look at. Another way to look at it would be with string theory, saying that they're actually interactions of gravitons. So gravity is the result of gravitons communicating with everything else in the universe. So now the really important conclusion, what all of this was leading up to, everything we've been talking about. So the idea of string theory is that every single fundamental particle are actually made up of vibrating strings at different oscillations, at different energy scales and different frequencies. And everything is made of these vibrating strings, and the way these strings vibrate give us different particles. So every atom is made out of protons and neutrons. Every proton and neutrons is made up of quarks, and quarks, string theory would say, are made up of these vibrating strings. So we talked about the unification of space and time. String theory would allow us to unify space and time and matter. Because it would not only be matter that's made up of vibrating strings, but it would also be gravitons, gravity itself, that are made up of vibrating strings. So an interesting thing to note is that the path of physics generally describing the world has always been more unification, more simpler, more kind of streamlined description of reality. And this is the appeal of string theory, that it would be mind-blowing and fascinating if we could actually find out that the world, we could unify space and time and matter itself being the same thing, all made up of vibrating strings at different frequencies. So it took a while to get here, but I hope it was worth the journey, and I hope you found out something interesting. So If you have any thoughts about this video, please let me know in the comments, and of course, thank you so much for watching and take care.